Hello everyone, today we will explain the vehicle passability analysis feature in the road surface module. To analyze vehicle passability, trajectory files are required. First, create a new project and add the trajectory file. This feature simulates the vehicle's movement based on the regular triangular mesh of the road surface, along with the trajectory data and the vehicle size information. It then detects collisions within the road to ensure safe passage of vehicles. For example, this analysis can determine whether a large truck can safely pass through a bridge or road with dense vegetation. To begin, activate the vehicle passability analysis feature. You will see options for trajectory and vehicle in the dialog box. If you have specific requirements for the vehicle mode, make sure to prepare the vehicle size data beforehand. Next, select Vehicle. You will see the software's built-in vehicle models, with the default being the front of a tractor or another integrated vehicle body. The default for the trailer is the trailer of a tractor. If it is a passenger car, SUV, or an integrated truck, leave the trailer field empty. Then click the Vehicle Designer button to open it, where you can see the software's built-in parameter files and model displays for the main vehicle and trailer. Click the New button and enter the actual size data in the information module. Then click Save to instantly refresh the vehicle list with the newly created vehicle type. If you find any errors in the parameter input, simply left-click on the name list and the right side information panel will display the size data in real time. You can directly modify the parameters in the information panel. After making the necessary changes, click Save Changes to complete the modification of the size file. If you don't need a particular model, you can use the left mouse button to select a vehicle file from the vehicle size list, then click the Delete button to remove the size file. However, please note that built-in files cannot be modified or deleted. When everyone is working on a project and analyzing different roads, but the vehicle size are identical, one person can change the vehicle size models and export the vehicle model size file. The exported file will be in XML format, which other team members can copy and import. This way, when analyzing the passability of different roads using the same vehicle model, it ensures consistency in vehicle sizes for everyone. Once the vehicle sizes are prepared, the next step is to collect the trajectory segment. Click on Trajectory, and in the Trajectory dialog box, click on the Select Trajectory button. Left-click to select the starting point of the trajectory segment. Drag the mouse to select the trajectory segment, and left-click again to select the endpoint. The vehicle's simulated movement will occur within this trajectory segment. Note that to ensure accurate simulation, please select a continuous trajectory segment without any U-turns. After selecting the trajectory range, click on the Passability Analysis button. Once the analysis is complete, you can see the vehicle model. By dragging the mouse along the selected trajectory segment, you can view the wireframe model of the vehicle and its state at the nearest trajectory point based on the current mouse position. During the simulation, if there is a collision with a point cloud, the vehicle's wireframe model will turn red and the collision points will be stored in the additional cycle attributes. After the simulation is completed, the point cloud view mode dialog box, select the additional attribute cycle color mode and choose vehicle crash points as the attribute. In the 3D window, you can see the collision points displayed using the chosen color bar. This allows you to identify locations where the vehicle cannot safely pass. You can save the results of the vehicle simulation analysis as a simulation file. The simulation results only record the vehicle's posture and do not include collision point cloud data. It is possible to load previously simulated results for reanalysis. For road sections with significant irregularities in the terrain, the vehicle's model movement may appear jittery and uneven during the simulation. This can result in less precise results. If higher accuracy is required, it is recommended to create a terrain representation of the road surface. To do this, you can use the Road Surface Key Points by Grid feature to generate evenly spaced key points on the terrain. To obtain an accurate irregular triangular mesh of the road surface, it is strongly recommended to classify the point cloud first. Activate this feature and select the category in which the ground points are located in the dialog box. The grid region can be defined by drawing a polygon or using an existing polygon to specify a specific area for generating the grid. Alternatively, the entire point cloud dataset can be used to generate the grid. According to your needs, you can select the corresponding grid mode. Since you already have drawn a polygon region, you can directly use the existing polygon mode and select the pre-drawn polygon vector object. There are two types for constructing tin key points: digital elevation model and digital surface model. The default is DEM. The grid size determines the size of each individual grid cell when generating key points using a uniform grid pattern. Above and below are used in conjunction with the grid area. They help to capture the three-dimensional region above and below the grid area. Please refer to the diagram below for specific details. The search radius represents the distance within which each grid key point needs to search for surrounding point cloud data during ground fitting. Based on experience, it is recommended to keep the default values for the parameters mentioned above. The to class refers to the category where the detected key points will be stored. By default, they are stored in the Model Key Point class. You can choose a different class based on your requirements. When the contour option is selected, key points will be generated along the contour lines of the polygon. If it is not selected, key points will only be generated at regular grid points. Clear regions is used to clear selected custom grid polygons and previously selected polygon regions. After setting the parameters, click Detect. Once the detection is complete, the point cloud will be displayed according to their categories. Only the Model Key Point class will be shown. Check if the key point results are reasonable and error-free. For any erroneous areas, you can use the Attribute Classification tool to reclassify categories, clear key points, or manually correct them. Assuming the key points are correct, proceed to construct the tin. Make sure the key points are accurate and complete in order to obtain a proper row tin. Activate the Create Tin function. In the dialog, select the range of key points to be used for tin construction. You can choose all existing key points or define a new polygon region. The key points within the selected area will participate in the tin construction. For the key point class parameter, choose the class that includes the key points for the tin construction. In this case, select the Model Key Point class. The minimum edge length refers to the threshold value to delete any triangles in the tin mesh that have an edge shorter than the specified length. When combined with the maximum edge length parameter, it ensures that the generated tin does not contain excessively short or long triangles. The maximum edge length parameter represents the threshold for deleting triangles in the tin mesh that have an edge longer than the specified length. When combined with the minimum edge length parameter, it ensures that the generated tin does not contain excessively short or long triangles. By default, you can leave it as is. If you have specific requirements for this parameter, you can set it accordingly. Finally, click Create to initiate the construction process. Once the construction is complete, the tin will be displayed by default using the Display by Solid Model mode. The tin can be displayed in three different modes: Display by Solid mode, Display by Wireframe, and Display by Vertices. Display by Solid model shows the tin as a solid surface with opaque material. Display by Wireframe shows the tin as a wireframe displaying the edges of the triangular mesh. Display by Vertices shows the tin in its key points. If the tin construction results are not satisfactory, or if you want to reconstruct the tin, you can use the Clear All Tin function to remove all tin meshes from the current project. However, please note that this operation cannot be undone, so use it with caution. After constructing the tin for the road surface, you can proceed with vehicle simulation. Load the simulation file saved earlier and drag the mouse to view the wireframe model of the vehicle and its state at the nearest track point based on the current mouse position. You will notice that compared to the uneven road terrain, the vehicle's movement over the created terrain is relatively smooth. This leads to a higher accuracy in the final results. If the road terrain is relatively flat, you can skip the terrain creation step and directly analyze the vehicle model. That concludes the introduction to the Vehicle Accessibility Analysis feature. Thank you for your attention.